Hello everyone, I am Bhrugrish Mishra from IIT Bombay, and this is the online session of elements of solar energy conversion for week 3 lecture. So in this lecture, in this online session I'll cover these topics: the radiation prediction, direct and diffuse radiation, hourly and daily global radiation ratio, and also the calculation of hourly and daily global radiation on a tilted surface. So first we will just briefly look what are the terms, what are the formulas which is studied in the lecture, and then we'll take a problem to solve, like we'll take a problem where we will use these formulas to solve to predict the hourly as well as daily average solar radiation, direct and diffuse, both on a horizontal plane as well as on a tilted plane. So uh, first we will look the important angles, like the angles are very important for this course, and we need to mesmerize these angles so that we can use it whenever we want, and we will not have any doubt regarding the angle. So the angles are very important. This sun earth relationship and the angles depicting or describing the position of the sun rays incident on the earth's surface, and accordingly the projection of the sun rays on the horizontal surface or whatever the surface we are considering, for example solar cell. Okay, so these things is very important. So suppose I have a surface here, like we have all see these things, already saw these things in the previous lecture. This is just to give you again an overview if you might have forgot. So this is a surface. Okay, so this is a surface, and suppose this is, since it is a since suppose it is tilted with respect to horizontal by an angle of beta. So beta is the tilt angle of this surface. Now if I draw the normal on this tilted plane, it will be look like something like this, and again the normal to the horizontal plane will be like this. So this is normal to the horizontal plane, and this is normal to the tilted plane. And if I depict the directions, say this is north, south, here it is east, and it is west. So for example, sun is here somewhere. Okay, also say the projection of the normal of this tilted plane on the horizontal plane. So it is, for example, like this. So it will look like this, and this angle is called the azimuthal angle or surface azimuthal angle. Okay, now projection of, so suppose the sun rays are hitting to the surface like this. So the angle of this sun ray make with the normal to the tilted plane is the incident angle theta, okay, with respect to the normal to the tilted plane, and the zenith angle will be this one, with respect to the normal to the horizontal plane. So it can also be depicted as theta I means incident. So when beta is 0, theta I will be theta z. Okay, so when beta equal to 0, theta I is nothing but theta z, that is zenith angle. Okay, now if we take a projection of this sun ray to the earth, to the horizontal plane, it will look like this. Okay, so the angle it makes with the south, this one, this is called the solar azimuthal angle, AZS. So here, and this angle, this angle is called the alpha, solar altitude angle. So this we have already looked. I'm just giving you an overview to refresh your memories, and we need these things in almost every lecture, so it will be habitual for you guys also to just draw the angles so that you can understand it in a better way properly. Okay, so here AZ is the azimuthal angle. It is also sometimes called surface azimuthal angle, and AZS is solar azimuthal angle. Theta is the incident angle, theta z is the zenith angle, alpha is the solar altitude. Okay, so what are the angles which we have looked up like these are the normal angles. Other than these, we have also looked at the latitude angle L, declination angle delta, and there are two more angles which were discussed in the class, that is the hour angle and sunrise sunset angle, hour angle basically. So omega or omega s. So omega is basically the angular measure of time. Okay, it is nothing but the angular measure of time, and it is equivalent to 15 degree per hour. This omega s is the hour angle corresponding to sunrise or sunset. So this omega s is measured with respect to the sunrise or sunset. Okay, so at sunrise you can say it is 0, starts from 0, then go to 90, then again 90 to 0, or 90 to minus 90 I can say. I can check it, just a minute. Yeah, so sorry, at 6 a.m. in the morning it is minus 90, at 12 noon it is 0, and then again at 6 p.m. it is plus 90. So basically if we consider noon as the center point where it is 0, in the morning it is considered negative, and in the afternoon it is considered as positive. So omega s varies from minus 90 less or equals to omega s less or equals to plus 90. In the morning it is negative, in the morning omega s negative, in the afternoon omega is positive. But different you will find different sign convention in different books, so you just have to stick with one sign convention whatever you use. Okay, but make sure that the other sign convention will also be according to that. Okay, so now if I if I want to calculate this incidence angle, okay, so when beta equal to 0, theta is theta z, so cos theta, so when beta equal to 0 means the horizontal plane is the like tilted plane is so tilted angle is basically 0, so that means the angle between the plane and earth is 0, so it is lying on the surface, not have any angle with respect to the surface. Okay, so in that case theta equals to theta z, so cos theta z can be calculated with respect to latitude, declination angle and the hour angle. So cos theta z equals to cos L, L is your latitude angle, cos omega, omega is the hour angle, cos delta plus sin L, sin delta. For tilted surface, theta z for the tilted surface, L simply be replaced by L minus beta, so the formula will be, and here it will be cos theta t, here t is tilted, cos L minus beta, and everything will be same, cos delta sin L minus beta sin delta. Okay, so and similar we can also calculate the sunrise sunset hour angle corresponding to sunrise sunset, which is omega s, and it is equal to cos inverse minus tan L tan delta. Okay, now in order to predict the solar radiation we need the formula. So the linear radiation the linear relation we use to predict the solar radiation, average solar radiation coming either hourly or daily basis or even monthly average also. So for that the formula is h bar by h naught bar equals to a plus b times SA bar by SP bar. Here h is the daily radiation which we are getting, daily radiation which we are getting, h bar is the monthly average, h naught bar is the monthly average of extra terrestrial radiation A and B are constant. Here SA bar is the sunshine hour, the monthly average sunshine hour given for that location, and SP bar is the maximum sunshine hour. So SP bar can be calculated as since like from sunrise to sunset, omega varies from minus omega s to 0 and then 0 to plus omega s. So total it is 2 omega s, and since we need sunrise hour in hours and omega is in degree, so we need to convert from degree to angle. So it is nothing but 2 omega s by 15. 2 omega s means from sunrise to sunset, and by 15 since 1 degree 15 degree equivalent to 1 hour. It can also be written as 2 by 15, and simply putting this omega s formula, which is cos inverse minus tan L tan delta. Okay, so for a given location we need to calculate H naught, SP bar, and AB constant will be given for that particular location, and SA bar will also be given. We need to calculate SP bar, and then accordingly we can calculate H bar, that is the total solar radiation coming on the surface, which is basically the monthly average. Okay, now in order to calculate the monthly average, we need to pick a day which we can represent as a which we can represent to calculate the monthly average solar radiation. Okay, so what we need to do is need to pick a day on which the radiation on that day is equivalent to the monthly average of the entire monthly average of the entire month. So we need to calculate a radiation on a particular day, and we need to check whether the radiation on that day is equivalent to monthly radiation, monthly average radiation of that particular month, and if both are matching, then we can represent the radiation on that day as a monthly average radiation of the entire month. Okay, so the list has been given in the lecture, and you will also find it in the several books. So we will proceed to the question. Okay, so I have picked a question from Sukhatme book. So the question is, use the prediction equation to calculate the variation of monthly average this is the wrong question. Use the prediction equation to calculate the variation of monthly average daily global and diffuse radiation falling on a horizontal surface at Bhavnagar, whose coordinates are given as 21 degree 45 minute north, 72 degree 11 minute east, during month of January, the monthly average sunshine hour is 9.8 hour. So this is the question. Okay, so the location is Bhavnagar, latitude is given as 21 degree 45 minute north. First we need to change this minute into degree, so it will be 21 degree plus 45 by 60 degree north, so it will come around 21.75 degree 21.75 degree north, yeah, or simply 21.75 degree. Okay, now here the month is we need to calculate the monthly average daily global for the month of January. So if we say for the month of January, which day represents the monthly average daily global and diffuse radiation, so we found that for January the day which depicts the monthly average daily radiation is n equals to 17. So all the calculation will be done for n equals to 17. Okay, now so the formula is h bar by h naught bar equals to a plus b SA bar by SP bar. So for Bhavnagar, the coefficients A and B are given as A equals to 0.28, B equals to 0.47, and from question it is given that SA bar equals to 9.8 hour. Okay, so we need to calculate, find H naught bar and SP bar. Okay, so first we need to calculate the declination angle. So first let's calculate SP. So for SP is 2 omega s by 15. So we need to calculate omega s, and omega s is given as cos inverse minus tan L tan delta. So we need to calculate delta first, that is the declination angle, and since we know the n is 17, we can calculate the delta for that day. Okay, so how to calculate delta? The formula for delta is 23.45 sine 360 by 365 284 plus n. So if you put n, the value comes out to be around minus 20.916, and round off value is minus 20.92 degree. So delta is minus 20.92 degree. So we can calculate omega s as omega s equals to cos inverse minus tan. L is the latitude angle which is given 21.75 degree, tan 21.75 degree, and we also calculated delta which is tan minus 20.92 degree. Okay, so omega, if we calculate this value, it turns out omega is equals to around 81.23 degree, and if we convert it in the radian, it is around so 81.23 into pi by 180, and if we calculate this value, just a minute, so 81.23 into pi value is 3.14 divided by 180, so it is around 1.147, sorry, 1.417 radian. So somewhere we can use the omega s in the degree, and we also need it as a in radian, so we have calculated both. Okay, now we have the omega s, we can calculate the SP, or same I can say SP bar. So SP bar is 2 omega s by 15, and now omega s is 81.23, so 2 into 81.23 divided by 15, and it comes as around 10.83 hours. So 10.83 is the maximum average monthly sunshine hour for the month of January. Please note that it is a sunshine hour. Okay, that means the maximum hour in which sun will be in the sky, like it is sunrise or it is not, so that the time duration between sunrise and sunset. Okay, that is the SP represents in hours. Okay, so now we need to calculate the H naught bar, that means the monthly average extraterrestrial radiation. So for the H naught we need to so the formula for H naught is so let's calculate first how to calculate the H naught. So we know the extraterrestrial radiation coming, like intensity. So intensity on a normal plane in extraterrestrial location, and it is here n depicts the normal, this n is the normal radiation, equals to ISC the solar constant, which is 1367 watt per meter square, and 1 plus 0.033 cos 360 n by 365. Now for the horizontal plane, so this is this is the radiation coming with respect to normal. Okay, and the angle is theta or theta z. So for the horizontal component will be I OH is nothing but I ON into cos theta h, and here theta h is theta z. Okay, so we have already noted down the formula for cos theta h or cos theta z. So you can write I OH equals to ISC 1 plus 0.033 cos 360n by 365, and the formula for cos theta z is cos L cos delta cos omega plus sin L sin delta. Okay, now we need, this is the hourly value. Okay, we need to calculate the daily value. So the daily value, for the daily value, this will be integrated from sunrise hour to sunset hour, or we can say the total sunshine hour. So let's say it is dt. Okay, so now we need to convert dt, since there is no t term here, time term, so we need to represent t in terms of omega, which is another way to represent time duration. So t will be 180 omega by 15 pi, or simply 12 omega by pi. So dt will be 12 pi by d omega. So you can write h naught as integration of ISC 1 plus 0.033 cos 360n by 365 cos L cos delta cos omega plus sin L sin delta, and now dt is 12 pi by d omega. Now all the things and the integration, now it is, since it is omega, in terms of omega, so the integration will be from sunrise hour angle to sunset hour angle, which is minus omega s to plus omega s. So it is minus omega s to plus omega s. The constant terms we can take out, so it will be 12 by pi ISC 1 plus 0.033 cos 360n by 365 pay out, and the omega dependence term will be left here. So it is minus omega s plus omega s cos L cos delta cos omega plus sin L sin delta d omega. Okay, so if we do the integration, we will find that this term will be equal to 2 times cos L cos delta, this will be sin omega s, and here also omega s sin L sin delta. This is a simple integration which can be done very easily. Okay, here cos omega will be sin omega, and since there is no quantity, so consider it is at 1. So that means integration of dw, which d omega, which is nothing but the omega. Okay, so the h naught is 24 pi ISC 1 plus 0.033 cos 360n by 365 cos L cos delta sin omega s plus omega s sin L sin delta. Okay, now we can so for the n equals to 17 here, n equals to 17, this h naught will represent the monthly average for the month of January. So for n equals to 17, h naught bar is 24 pi. Also since here the unit of ISC is in watt per meter square, and we need it for the joule per meter square per day, which will be the monthly average basically. So we need to convert the unit. So in joule per meter square per day, it will be 24 pi into ISC into 3600, 1 plus 0.033 cos 360n by 365 cos L cos delta sin omega s plus omega s sin L sin delta, which is in joule per meter square per day. Okay, the unit is joule per meter square per day. So now we can put all the values and calculate it. So it is 24 pi, this is 1367 into 3600, 1 plus 0.033, and this is cos 360 into 17 by 365, and the values L is L is 21.75 degree, delta is minus 20.92, sin omega s is 81.23 plus, now here this omega s, this will be in the radian, not in the degree, so it will be 1.42 into sin L, which is 21.75, and sin delta, which is sin minus 20.92. okay, if we calculate this value, I have already calculated it, but you can calculate it to check whether my calculation is right. So it will come out as h naught equals to 259776000 joule per meter square per day, and we can convert this in the kilojoule. Okay, so it will be 25977.6 kilojoule per meter square per day. Okay, so we have h naught, we have sp bar. Sp bar is calculated as 10.83 hour, A is 0.28, B is 0.47. so now we can calculate h bar as A plus B, and also SA bar is also given in the formula as 9.8 hours. So SA bar by SP bar into H naught bar, and if we put all the values, it turns out 18322 kilojoule per meter square per day. Okay, so this is the monthly average daily global for the month of January. Okay, now we also need to calculate the diffuse radiation. Okay, so what is diffuse? So basically in the atmosphere there are a lot of dust particles, aerosol particles. So when the solar radiation enters in the atmosphere, these particles scatter those incident solar radiation. So there are two type of scattering: relay scattering, which is why our sky appears blue, and Mie scattering. Okay, so the solar radiation which is scattered by the dust particles, aerosol concentration, or other molecules whose size is corresponding to the wavelength of the solar radiation, scatters. Okay, and thus it does not hit the surface at the so at the incident angle. Incident angle means so suppose sun is coming, sun is right now at the zenith of so not zenith, suppose the incident angle is right now around 40 degree. Okay, so if there is no scattering present, then all the radiation will hit the surface at 40 degree. But there are because of this scattering, some radiation will hit the surface with lesser intensity. Okay, not the intensity with the actual solar radiation which is hitting at exact 40 degree angle to the horizontal surface. So due to scattering, their intensity will be slightly low, I can say. So it will hit the surface at different angles. Okay, it will also scatter from the surrounding, or not only the dust particles or the aerosol concentration present in the atmosphere, but can also scatter from the surrounding material, surrounding anything. Even the ice can scatter or reflect the solar radiation. Water particle can scatter it or absorb it. Okay, so these the radiation which is not coming at the angle at which sun is radiating towards the surface, it's called the diffuse radiation, or simply the radiation which is scattered by the aerosol concentration or by the particles available in the atmosphere. That is called the diffuse radiation. So at very cloudy day, or when there is lot of dust in the atmosphere, then the diffuse radiation will be much higher. Not much higher, but yeah, it will have a greater amount compared to the direct radiation. Okay, also as solar radiation, as the sun is so sun is having a angle greater than a certain angle, around 60 degree, then also we will have a lot of diffuse radiation. So in the morning and at the sunrise and at the sunset, we will have more diffuse radiation compared to the direct radiation, because the light travels more path before reaching the earth, and thus it has higher chances to get scattered in the atmosphere. Okay, so So for the diffuse, direct and diffuse, we can calculate. So small d will represent the diffuse radiation, and capital D represent the direct radiation. So the formula for this is HD bar by H bar, which is the total monthly average global radiation, this H bar, and HD bar is the diffuse portion, equals to 1.411 minus 1.696 kT bar. Okay, this kT bar is the clearness index, and it can be calculated as kT bar is H bar by H naught bar. Okay, so here, and thus for the direct we can calculate is as HD bar by H bar equals to 1 minus HD bar by H bar. So thus H bar is nothing but HD bar plus H capital D bar, means the global is equal to diffuse part plus direct part. Okay, so since we know the value of H bar and H naught bar, we can calculate the KT, that is clearness index. So KT will be H bar by H naught bar, and H bar is 18322, and H naught bar is 25977. 25977.6. So the ratio of these comes as around 0.7053. So HD bar equals to it is 1.411 minus 1.696 into 0.7053 into H bar. So it comes out as 0.2148 into H bar, which is 3935 kilojoule per meter square per day. Sorry, this is HD, small hd, this is the diffuse part. So the direct part can be calculated as H bar minus HD bar, and it is 18322 minus 3935, so it is around 14387 kilojoule per meter square per day, so which is significantly higher compared to the diffuse radiation. Okay, so this way we can predict the monthly average of daily radiation at a particular location. Okay, now if we want to calculate the monthly average of hourly radiation, okay, so monthly average hourly global and diffuse radiation. Now for the hourly radiation we need to pick some hour angle. Okay, we can't, since it is an hourly angle, so we need to pick an hour angle, because we need to calculate the average hourly. Okay, average hourly means So for example, I'm saying that the average radiation coming in the in the month of January on from 10 a.m. in the morning, or from 9 a.m. in the morning to 10 a.m. in the morning. Okay, so example, want to calculate this monthly average hourly radiation in between 9 a.m. 10 a.m. So other parameters I'm keeping the same, that is n. So this is the month of January, so n equals to 17. So this 9 a.m. 10 a.m. will be at n equals to 17. Okay, so the for the monthly average, so we need to calculate omega is the hour angle. Okay, so need to, for calculating monthly average hourly radiation, we need to know the hour angle. Okay, for that particular hour for which we are calculating the radiation. So for such a span, we consider the middle value, or the middle time. That means for 9 a.m. to 10 a.m. the time which we consider for our calculation will be 9:30 a.m. Okay, so if you want to calculate the omega for this 9:30 a.m., so omega can be calculated as omega equals to 15 into st minus 12 hour. Here st is the standard time, okay, standard time in hours. So this is 9:30 a.m. okay, so 9:30 a.m. means it is simply 930 hour. Okay, 930 hour. So if we calculate omega for this case, it will come out to be 15 into 2.5, okay, which is 37.5 minus 37.5 degree. So this is the angle which we will consider. Okay, so here 9:30 can simply also write it as 9.5 hour. Okay, so 9.5 minus 12 is nothing but minus 2.5. That is why we are getting this minus 37.5. Okay, so now for the tilted for hourly average, there is a ratio which represents the radiation coming the hourly average radiation upon daily average radiation, and this equals to pi by 24 a plus b cos omega minus cos omega s by sin omega s minus 2 pi omega s by 360 cos omega s. Okay, so we already know the h bar we have calculated, and we know here omega s. This a and b is different from the a and b we have used in the calculation of daily average, monthly average global radiation. Okay, so this a and b can be calculated using this formula: a equals to 0.409 plus 0.5016 sin omega s minus 60, and b 0.6609 minus 0.4767 sin omega s minus 60. So we have calculated omega minus 37.5 degree, and omega s is 81.23 degree. So we can calculate this a and b. So it is 0.409 plus 0.5016 into sine of omega s minus 60, that means 81.23 minus 60. So a comes out to be around 0.59 and b 0.6609 minus 0.4767 into sine of 81.23 minus 60. So b is around 0.488. okay, and we also know h bar, which is 18322 kilojoule per meter square per day. Units are very important, so please make sure that you are using the correct unit. Okay, do not use somewhere kilojoule and somewhere joule. You have to be consistent and you have to be careful with the units. So now we can calculate. So I bar will be pi by 24, and we know is 0.59, 0.488, and we have calculated cos omega is, so omega is minus 37.5 minus, okay, and now this one cos minus 37.5 cos 81.23 sine 81.23 minus 2 into 3.14 into omega s in radian is 1.42 divided by 360 into cos of 81.23. Just a minute. So if we calculate this as a whole, so cos of minus 37.5 minus cos of 81.23 divided by sine of 81.23 minus 2 into 3.14 into 1.42 into cos 81.23 divided by 360. Okay, yeah, just a minute. So turns out, so this portion turns out 0.6509. Now I will calculate with the rest one into 3.14 into 0.59 plus 0.488 into cos of minus 37.5 degree divided by 24. So I bar is 0.083 into 18322 into 18322. So it is 1524.77 kilojoule per meter square per day. So that means from 9 a.m. to 10 a.m. okay, this is the monthly hourly, this is the monthly average of hourly global radiation incident on the given location. Okay, and similarly we can calculate the diffuse radiation. For the diffuse radiation the formula is quite similar. It is just so the ratio RD equals to ID by HD equals to pi by 24 cos omega minus cos omega s by sin omega s minus 2 pi omega s by 180, sorry, it's pi omega s by 180 into cos omega s. Okay, so it is almost, this portion is almost similar to this, and we have already calculated this, so we can calculate it right now as 3.142 by 24 into 0.6, sorry, 6509, and we have already calculated HD bar as HD bar as 3935. Okay, so it will be 3.142 into 0.6509 divided by 24 and into HD is 3935, so ID is 335.3 kilojoule per meter square per day. So that means this amount of diffuse radiation, hourly diffuse radiation we are getting for the given location. Okay, so the same way we can calculate for the tilted angle. You can do the entire process for the tilted angle of beta equals to say 15 degree. Okay, so for the tilted angle the entire calculation will be done for the latitude of L minus beta. Okay, so you can check you can do the this calculation again for this tilted angle, and make sure you are doing the correct thing, because there are lot of numerical steps involved, so you need to be very careful with the units, with the, like, somewhere you need to use angle in radian and somewhere in the degree, so need to be consistent. Okay, so yeah, that's it for the today. We'll meet in the next class. Thank you.